Hello everyone, welcome to IIT and GATE classes. This is lecture 20 on TOC, and in this lecture we are going to start closure properties of RE and REC languages. Okay, if you do not know about what closure properties are, so it's my kind suggestion, please watch my lecture number 8 and lecture number 16. In both these lectures I have discussed about closure properties. In lecture 8 I have discussed about closure properties of type 0, type 1, type 2, type 3 languages, and in lecture 16 I have discussed closure properties of DCFS. Okay, so directly and directly I want to tell you about, I have already discussed closure properties 2 times, and this is the third time I am discussing closure properties. And you may wonder that why I am discussing closure properties multiple times, because it is very important topic. In each and every competitive exam you will see direct question about closure properties of languages. Okay, so let me discuss about closure properties of RE and REC languages. So first operation is transpose operation, and I hope you remember what exactly is transpose operation. So let me revise you. Okay, so L transpose means what? W transpose such that W belongs to L. Okay, so directly and indirectly, what does this mean? This means that if W belongs to L, then W transpose will belong to L transpose. So that means what? We have transposed, or we have reversed each and every string in language L, then we will get L transpose. Okay. So how will you prove that both RE and REC languages are closed under transpose operation? This is very simple scenario, because see here carefully. For REC languages and for RE languages, okay, for REC languages we have a halting Turing machine to check W belong to L or not, and for RE languages we have a Turing machine to check W belong to L. Okay, so Turing machine may or may not halt, but halting Turing machine always halt and say yes or no. So in case of RE languages, if W belong to L, then Turing machine will halt and say yes, but if W does not belong to L, then Turing machine may hang also. Okay, so this is the basic scenario, you already know about it. Now directly and indirectly, both are actually Turing machines only, and in Turing machines we have a read write head which can move in both the directions. Since we have a read write head which can move in both the directions, so directly indirectly our work is over. Why? Because if see here carefully, if W is accepted by Turing machine and we say that we have already told na, Turing machine consists of tape of infinite length divided into cells. Okay, one symbol store one cell store one symbol at a time, and read write head is positioned to the first symbol of the input string. Okay, and string C, so we are scanning, or we are reading the string from left to right like this. Generally we are doing like this. Now in place of reading string like this, you can read string like this also. Okay, so in place of placing read write head on first symbol, place read write head on the last symbol. Okay, and in place of moving in place of scanning like this, you may scan like this also. That's it. So our work is over. So if W belong to L and halting Turing machine say yes, so for W transpose, obviously halting Turing machine will say yes, because now we will scan like this. Okay, of course it is not proper proof, I'm just giving you intuitive idea about why RE and REC languages are closed under transpose operation. So same is the case, I have told you about halting Turing machine, same is the case with Turing machine also, because directly and indirectly both are Turing machines now. So please do not go into do not dig deeper into these things, because this is a basic course and I'm not going in proper proof and all. I'm just giving you intuitive idea about why in transpose operation both RE and REC languages are closed. Bottom line is that in place of reading string like this, try to read string like this. That's it. Okay, so next operation is union operation. In union also both RE and REC languages are closed. This is you have to remember this fact. Okay, so please in the previous slide, please note it down carefully. I am dictating, I am not writing. In transpose operation both RE and REC languages are closed. Okay, next, in union operation both RE and REC languages are closed. We are not going into proof and all, because this is a basic course, but let me show you an intuitive idea about how will you prove that both RE and REC languages are closed under union operation. See here carefully. Okay, so my claim is that if L1 is REC and L2 is REC, then L1 union L2 is REC. Same is the case with RE also. Okay, so same is the case with RE also. So let me copy it. Okay, so yeah, so I will say here If L1 is RE and L2 is RE, then L1 union L2 is RE. Okay, yeah. So how I'm going to prove it? Okay, so let me just give you intuitive idea. I'm not going into detail because this is a basic course. So what I will say, okay, so for REC we have a halting Turing machine, for RE we have a Turing machine. So directly and indirectly we have Turing machine for both these languages. So let me show you for REC languages. See, uh, for L1 you should have a halting Turing machine 1 which can accept it. Okay, or let me show you with a different color so that you get proper clarity. For L1, you have a halting Turing machine 1 which can accept it. For L2 you have a halting Turing machine 2 which can accept it. Okay, so now I want to say L1 union L2 is also REC. That means for L1 union L2 you should have a halting Turing machine. Okay, so what I will say is, okay, so in place of L1 or L2, okay, so see, I am saying it just to give you intuitive idea. I'm not going into proper proof. I'm just saying for halting Turing machine 1 is for L1 and halting Turing machine 2 is for L2. Now what will you do? We will construct a big halting Turing machine HTM, okay, which internally call these two Turing machines as a function. Okay, and we will give this W to halting Turing machine, and this W will be given implicitly to halting Turing machine 1 and halting Turing machine 2. Okay, if any one of say yes, because this is halting Turing machines now, so both will say either yes or no. Okay, so if any one of say yes, then halting Turing machine will say yes, but if both of these say no, then halting Turing machine will, this big halting Turing machine will say no. So for string W we have constructed a big halting Turing machine which is saying yes as well as no. Hence your L1 union L2 is REC. Okay, so I hope I have made the point clear. If you are not able to follow, please just leave it. I am just giving you intuitive idea. That's it. Similarly, we can prove for RE also. Okay. Next is concatenation operation. Similar idea. Both these languages will be closed under concatenation operation. Say similar idea. Okay. So I will say that L1. Okay. Let me show you with a different color. L1 is REC. L1 is REC. L2 is REC. Then I will say L1 dot L2 is REC. This is our claim. Similarly for RE also. So I will just construct a big Turing machine, which will, if I will say W, okay, so I will give this W to this big Turing machine, okay, and it will divide it into two parts, W1 and W2. Okay, so W1 and W2, and W1 will be given to say halting Turing machine 1 and W2 is given to halting Turing machine 2. Now if both will say yes, then your big Turing machine will say yes. Okay, if any one of say no, then it will say no. Okay, so I hope you remember about what exactly is concatenation operation. So concatenation means what? See, actually please actually now video will become longer and longer, and if you do not know about concatenation operation, then watch my lecture number 8. You will get crystal clarity about what exactly is concatenation operation. So the bottom line is you have to remember both RE and REC languages are closed under concatenation operation. That's it. Okay, and you need not go into proof and all because this is a basic course. In advanced course I will tell you about proper proof and all. Okay, next operation, intersection. Same is the case. In intersection both will be closed. Okay, both RE and REC are closed. REC are closed. You can build a similar idea here also, like union. You will have you can make a similar Turing machine. Okay, in intersection I will say if both say yes, then it will say yes. If any one of say no, then it will say no. That's it. Okay, so I hope I have given you a bit idea about why in intersection both are closed. Okay, next is complement operation. See here carefully. In complement operation, REC languages are closed, but RE languages are not closed. So let me give you a small intuitive idea about why REC are closed and why RE are not closed. Okay, so you already know what is L complement. L complement consists of all those W's such that W does not belong to L. Okay, so if L is, I am claiming that L is REC implies L complement is REC. Okay, how will you claim it? How will you claim it? I will simply say we have a see if L is REC na, so I will give W any string W to halting Turing machine 1. Okay, I will give W to halting Turing machine 1. Okay, and this Turing machine 1 will internally call a small Turing machine. Okay, so let me show you properly. Okay, otherwise you will get confused. Okay, so I am claiming that if L is REC, then L complement is REC. Okay, so if L is REC, then for L we should have a halting Turing machine. Okay, now I want to claim if for L we have a halting Turing machine, then for L complement also we should have a halting Turing machine. Okay, so let me build a intuitive idea. Okay, so I will give W to a big Turing machine HTM. Okay, and this HTM will internally call HTM1. HTM1. Okay, and this W will be given to HTM1. If HTM1 say yes, your big Turing machine will say no. If HTM1 say no, your big Turing machine will say yes. So directly, indirectly, I have given you a hint. Okay, so please try to follow it. For because L is REC, so for that we should have a halting Turing machine. Now I'm trying to build a halting Turing machine for L complement. So how I'm building? I'm saying that we have a big Turing machine HTM. Okay, so I have given this W. I have given this W. Okay, I have given this W to this big halting Turing machine, and it internally calls a small Turing machine HTM1, which is for your L. HTM1 is for L. Now W is given to HTM1. If HTM1 say yes, your big Turing machine will say no. If HTM1 say no, your big Turing machine will say yes. So directly and indirectly, we have constructed a halting Turing machine. Hence, REC are closed under complement operation. What about my RE? See, RE, there will be a small problem here. Okay, let me show you how. Please note it down carefully. Now I will say if L is RE, then L complement is RE. I want to claim this thing. So we have to construct a Turing machine. So for so here also we will have a Turing machine. So Turing machine will call this Turing machine 1. Now see here carefully. Turing machine, big Turing machine will call this small Turing machine 1. If W belong to L, then it will say yes. So obviously your big Turing machine will say no. There is no problem. But in case of no, Turing machine 1 may hang. Turing machine 1 may hang, and I am writing a question mark here for no. So for yes, we will have a question mark. So directly, indirectly, we have constructed a Turing machine which is saying no, but it is not able to say yes. So, but language is RE. Why? When we say language is RE, no doubt we have constructed Turing machine. But when we say language is RE, we have a Turing machine to accept it. To accept it. That means Turing machine will say yes, but this Turing machine is not saying yes. So directly, indirectly, we are not able to construct a Turing machine which can say yes. Hence, RE are not closed under complement operation. Okay, I hope I have made the point clear, because according to definition of RE, I am not saying anything. I'm just saying, try to remember definition of RE. For definition of RE was there should exist a Turing machine to accept L. That means we are caring about members. So if W belong to L, then Turing machine will halt and say yes. But here, if W belong to L, then because W should belong to L transpose, na? Sorry, L complement, na? Okay, so if see here carefully, if W belong to L, then W will not belong to L complement. But if W does not belong to L, then W should belong to L complement. Okay, I'm writing this. W belong to L implies W does not belong to L complement. W does not belong to L implies W should belong to L complement. Now, we have a string W which should belong to L complement. Okay, but we are not able to design Turing machine which can do this task. Okay, so if W, I'm assuming that W belong to L complement. Okay, I'm assuming that W belong to L complement. So W does not belong to L. Now I have given this W to this Turing machine. So this Turing machine will must say yes now, but it will not be able to say yes. Why? Because this Turing machine will internally call this Turing machine 1, and I have already told you that W does not belong to L. See here carefully. W does not belong to L. So Turing machine 1 is now free to say no, or it may go to hang. Now, if this go to hang, then how it will say yes? I hope I have made the point clear. This is a bit difficult point. Try to follow it. If you are not able to follow, don't worry. Please just try to remember this fact that in complement operation, REC languages are closed, but RE are not closed. Okay. Now let me put everything on one slide so that you can note it down. Yeah, I am jumping to next slide now. Proof is not important. The main thing, because this is a basic course, so the main thing is you should remember about all these things, that why or you should remember that REC are closed under complement, but RE are not closed under complement. Okay. Next slide. See, there are 4 possibilities. Okay, so because we have discussed about complement operation, so there are 4 possibilities. 4 possibilities means what? See, we have already told you about REC and RE languages. Okay, watch my previous lecture if you are not able to follow what exactly are REC and what exactly are RE. So I have constructed a Venn diagram, and I am saying that REC are closed under complement operation. That means what? Both L and L bar can be here. Okay, we have a language L, and obviously we will have a L complement also. So both can be inside like this. One can be here RE if language is L, if L is RE but not REC, then L can be here. L complement should be outside. Okay. Next, both can be outside, but this scenario both are inside. This is not at all possible. Please try to remember this. Okay, this is very important theorem. I'm not going into proof, but I just want to tell you that both L and L complement are RE but not REC. This is not possible. Okay, both L and L complement are RE but not REC. This is not possible. Both L and L complement are RE but not REC. This is not at all possible. So we have only 3 possibilities. Possibility number 1, possibility number 2, possibility number 3. This is not at all possible. Okay, because if both L and L are see, if question came both L and L are if both L and L bar are RE, then actually both will be REC. Okay, so let me write this line also. If both L and L bar are RE, then actually L and L bar must be REC. Must be REC. Okay, so this is indirectly a hint to you that if question says L and L bar are RE, that means what? You will say that L and L bar must be REC. Okay, so it cannot be the fact that both L and L bar are RE but not REC. This is not allowed. L and L bar are RE but not REC. This is not allowed. Okay, I have already told you that both L and L bar are RE but not REC. See here, this is not allowed. Okay, see my hand. This is not allowed. Not at all allowed. Okay, this because why this is not allowed? Because if both L and L bar are RE but not REC, that means what? For L we are see, L is RE but not REC. That means what? We have a Turing machine which will say yes, but in case of no, it may hang. Now L bar is RE but not REC. That means what? For L bar we will say yes. Okay, let me tell you or let me give you a brief proof about this. Actually, I do not want to go into proof and all because this is a basic course, but I'm not able to control myself, so I'm giving you just intuitive idea. See, L is RE but not REC. L is RE but not REC. What does this mean? This means for L we should have a Turing machine which will always say yes, but in case of no, it may go to hang. Similarly, I am saying L bar is RE, but not REC. So for L bar, we should have a Turing machine which will say yes, and in case of no, it may go to hang. Okay, this is the case. Now I will say I have constructed a Turing. See, I am giving W to this big Turing machine. Okay, now if W, see, let me label it as Turing machine 1 and let me label it as Turing machine 2. Now this Turing machine will internally call Turing machine 1 and Turing machine 2. Okay, so now W will be given to both these machines. If Turing machine 1 say yes, then your actual Turing machine will say yes. If Turing machine 2 say yes, your actual Turing machine will say no. So that means what? For L, I have constructed a halting Turing machine which is saying yes as well as no. So directly indirectly means what? L should be REC. So this is a small proof. If you are able to follow, then it's okay. Or if you want to rewind the video, then watch it again. But I'm not going to repeat it. Okay. So please try to follow this. Okay. But if you are not able to follow, then just leave it. Okay, I'm just I have just given you idea, because this theorem is very, very important, and the questions, many times questions have been asked in GATE as well as NET. Okay, in various competitive exams, this question has already came. So so there are only three possibility. L and L bar both are REC. L is RE, but L bar is outside RE, that is known RE. Okay, and both L and L bar are known RE. Or this scenario, that is L and L bar both are RE but not REC. This is not at all possible, because if you are claiming that this is possible, then I have already told you that they will become here. They will come here itself. Okay, because if L and L bar are both RE, then intuitively you will say that for L we have a Turing machine, for L bar we have a Turing machine. Now, if Turing machine one say yes, then you will say yes. If Turing machine 2 say yes, then you will say no. That's it. Okay, so I hope I have made the point clear to all of you. So let me put everything on one slide so that you can note it down carefully. Yeah. So now I'm jumping to next slide. Set difference operation. You already know set difference means what? L1 minus L2 means what? L1 intersection L2 complement. So in intersection as well as complement, if language is closed under both operations, then in set difference it will be closed. Otherwise, it won't be closed. What about my REC? REC is closed under both intersection and complement. So REC will be closed under set difference. What about my RE? RE is not closed under complement operation. Hence, RE will not be closed under set difference operation. That's it. Please note it down. Yeah, union with regular, all types of languages are closed. So you have to remember RE and REC will be closed. Intersection with regular, you already know both are every type of language is closed under union and intersection with regular. So RE and REC languages will be closed. Okay. So next, now we are jumping to sixth topic of your fourth chapter of your TOC, that is Turing machines and decidability. So sixth topic is countability. Okay. So let me revise you. We are in chapter 4 of TOC. We are in chapter 4 of TOC, and we have already completed 5 topics according to syllabus. If you are not aware about syllabus, then please watch my lecture number, I think 18. In lecture number 18, I have discussed syllabus of your chapter number 4, that is Turing machines and decidability. Okay, so 5 topics are already over. Now we are jumping to 6th topic, that is countability. So you already know sets are of two types, finite and infinite. If set is finite, then it will be always countable. And if set is infinite, then it can be countably infinite or uncountably infinite. Okay, please try to note it down, and I'm jumping to next slide. Yeah, I hope you have noted down. I'm jumping to next slide. Okay. Yeah. So okay. So CI means CI means countably infinite. UCI means uncountably infinite. So what are these? Please don't worry. I'm going in detail slowly. Okay. So next is, what exactly are countable sets? So a set is said to be countable if and only if there exists one-to-one correspondence between given set and any subset of natural numbers. Please note it down carefully. I am saying any subset of natural number set, and there exists one-to-one correspondence. One-to-one correspondence means bijection. Okay. So if you do not know about functions, then it's my kind suggestion, please try to read about functions first and then come to this lecture. Otherwise, you will get confusions. So there must exist one-to-one correspondence. Roughly, you already know what exactly is one-to-one correspondence. Okay, so let me say it here for you. One-to-one correspondence means what? Like this. Okay. So each and every element of one set is mapped to exactly one element of next set, and directly indirectly one-to-one correspondence means what? Cardinality of both these sets must be same. Okay, only then we can establish one-to-one correspondence, otherwise we won't be able to establish one-to-one correspondence. Okay, yeah. So a set is said to be countable if and only if there is just one-to-one correspondence between given set and any subset of natural numbers. Okay, so now let me tell you something, that why I have said that every finite set is countable. See, you take any finite set, so I will take a finite subset of natural number, okay, of same cardinality, and I will try to establish one-to-one correspondence between them, and hence every finite set will be countable according to definition I'm saying. Okay, so let me tell you a brief or small example. Let me tell you a small example. We have a set S. In set S, okay, we have say few names like Ram, Sham, Sita, Geeta. Now I'm saying you that this set is countable. Why? Because I will pick a subset of natural numbers, that is 1, 2, 3, and 4. Okay. We have picked this subset of natural number set is infinite. 1, 2, 3, 4, 5, 6, 7, 8, and so on up to infinity. And I have taken a subset of natural number of cardinality 4. And I will write here as Ram, Sham, Sita, Geeta. Okay. And it's your choice. You map one with Ram or map one with Sham and so on. It's your own choice. So I am mapping like this. Okay. So I will say I have established a one-to-one correspondence between a subset of natural number and this set of 4 elements. So I will say that this set is countable. Okay, so directly indirectly you have got the proof that why every finite set is countable, because if that set is finite, no matter you have 1 lakh element, 10 lakh element, I will take a subset of natural number of 10 lakh numbers. Okay, so 1, 2, 3 up to 10 lakh, and I will try to establish one-to-one correspondence between 1 to 10 lakh numbers and that set having 10 lakh elements. Okay, I hope I have made the point clear to all of you. Okay, so just try to note it down on a faster manner, and I am jumping to next slide. Okay. Please note it down carefully. Yeah, so I'm jumping to next slide. Yeah, so every finite set is countable. I have given you proof in the previous slide itself. Okay, yeah, let's jump to next slide. So natural number set, integer set, and Z is integer, positive, negative integers, and Q is rational numbers. Okay, rational numbers means what? You already know about it, P by Q form, and Q should not be equal to 0. Okay, so P by Q form. Any number which can be represented in the form of P by Q and Q should not be equal to 0. These all are countably infinite sets. Okay, these all are countably infinite. Natural number set is obviously countably infinite because I have given you definition of countable set. Okay, so obviously one-to-one correspondence, we can establish one-to-one correspondence between natural number and natural number set. Okay, so this is very basic thing. So this will be your so hence natural number set will be countably countable. So, and because it is infinite, so I will say it countably infinite. Okay, obviously I can establish one-to-one correspondence between natural number to natural number now, because these two sets are same. Okay, now this is interesting part. How will you establish one-to-one correspondence between natural number and integer set? Okay, so see here, this is natural number set 1, 2, 3, 4, 5 dot 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 up to infinity, and this is your integer set. So I will say here 0, then 1, then -1, then 2, then -2, then 3, then -3, and so on. I will list all these integers like this. So I will say I have mapped 1 with 0, 2 with 1, 3 with -1, 4 with 2, 5 with -2, and so on. Okay, so directly and indirectly I have established one-to-one correspondence between integers and natural numbers. So so integer set is also countably infinite. Okay, because obviously Z is infinite and I have shown you countable, so it will be countably infinite. You may wonder that integer set should be exactly double of natural number, and you have told that for one-to-one correspondence, cardinality of both set must be same. But actually, it's your illusion that integer set will be double as of natural number. It's not the case because both are infinite. So we do not know about what exactly is infinity. Infinity is a concept. It is not a number. So they are just moving. Okay. So I will say that roughly that these two sets are of equal cardinality. You may think that both are different cardinality. Rather, integers should be double as of natural number, but both are equal because I have just established one-to-one correspondence between them. Okay. So if you are not able to follow, don't worry. Just try to remember the fact that integer set is countable. Okay. Or you should say countably infinite. And I have tried to establish one-to-one correspondence also. Okay. Now, what about my set of rational numbers, that is P by Q form? Okay. So just try to think about it. Why rational numbers or P by Q form is countably infinite? Okay. So let me give you just intuitive idea. Okay. So you may think that see one. Okay. So 1 by 1, 1 by 2, 1 by 3, 1 by 4, dot 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 dot. So you will say that, sir, try to establish one-to-one correspondence like this. This is your natural number set, and this is your set of rational numbers. So 1, 2, 3, 4. So 1 will be mapped with 1 by 1, 2 will be mapped with 1 by 2, 3 will be mapped with 1 by 3, 4 will be mapped with 1 by 4, and so on. So now my question is, what about my 2 by 1 or 2 by 2? You won't be able to reach 2 by 1 if you map like this. Okay, because actually there are many conditions which we have to follow about countable sets. I am just giving you idea that this is not the good way to establish one-to-one correspondence between natural numbers and rational numbers, because 2 by 1, what will be the natural number corresponding to 2 by 1? You will say, sir, infinite. But actually infinite is not a natural number, and in fact infinite is not a number. Okay. So one-to-one correspondence means what? You should be able to say that this is your number and it is mapped with this, then this natural number. Similarly here, if you say -1, I will say -1 is mapped to 3, 1 is mapped to 2, and so on. So you just name an integer and I will say that it is mapped to this and this natural number. But here I am not able to show it. So this is not the good idea. So let me cross it. Okay. So what is the better idea? I will say, roughly I am telling you, I will say try to sum them up. Okay. So I will say 1 by 1 will be the first, then 1 by 2 and 2 by 1. Okay. Sum is 3 na. Sum is 3. That means 1 plus 2. See here carefully. 1 plus 2 and 2 plus 1. Sum is same na. So you will say that I will map like this. Next, say I will say 3 by 1, 1 by 3, 2 by 2. Okay, because sum is 4. 3 by 1, 1 by 3, 2 by 2. Sum is 4, and so on. So I will try to map like this. So this will be natural number 1, natural number 2, natural number 3, 4, 5, 6, dot 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 dot. Okay, I'm just giving you rough idea about why rational number set is countable. So I have established one-to-one correspondence like this. So now you just try to name any rational number and I will say that its corresponding natural number will be this and this and so on. Okay. So I hope I have made the point clear. So if I cover rational number in this manner, then I will be able to reach every rational number in a finite amount of time, or you can say finite numbers will be before that rational number. Okay. So I hope I have made the point clear. And anyway, if you are able to follow, then it's good. If you are not able to follow, just leave it. You have to remember the fact that rational number set is countably infinite. Okay. So let me try to put everything on one slide so that you can note it down carefully. Okay. So next, I'm giving you a small claim that every subset of countable set is countable, and it's obvious also. Why? Because if the given set is countable, then I am taking a small subset of it. Okay, or I am just taking a subset of it. So obviously, if this big set has one-to-one correspondence with natural number set. So let me label this set as S. So I have established one-to-one correspondence between natural number and this set. So obviously, I will be able to establish one-to-one correspondence between a small subset of it, and I will take obviously subset of natural number. So obviously, every subset of countable set will be countable. I hope I have given you intuitive idea. Okay. So now I will take a very big advantage of this fact that odd natural number will be set of odd natural number will be countable. That means what 1, 3, 5, 7, 9, dot, 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 dot. This is countable. Even natural number is also countable. 2, 4, 6, 8, 10, dot, 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 dot. This is also countable. Prime numbers is countable. Okay, 2, 3, 5, 7, dot, 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 dot. This is countable. Why? Because it is subset of natural numbers. Okay, even natural number obviously subset of natural number, odd natural number obviously subset of natural number. All these are countable. What is this z plus? Z plus is positive integers. Obviously it will be countable because it is subset of integers. And I have already established one-to-one correspondence between integers and natural numbers. See here carefully. Integers and natural number, I have already established one-to-one correspondence. So I have taken a small subset of z, and I will obviously able to I will be able to establish one-to-one correspondence between natural number and that set also. And by the way, z plus is nothing but your natural number set itself. Okay, so obviously we will have one-to-one correspondence. Similarly, z minus subset of z, it will be countable. Q plus positive rational number, Q minus negative rational numbers, all these will be countable. Okay, and obviously all these are countably infinite. Okay, so all these are countably infinite. Okay, so let me put everything on one slide so that you can note it down carefully. Okay, so let's jump to next slide. Set of real number is uncountably infinite. So I'm not going into proper proof. For proper proof, I have to give you diagonalization or Cantor's argument. I'm not going into that, but I'm just giving you idea about real numbers is uncountably infinite. Okay, and let me give you intuitive idea about what exactly countability means, and then I will give you intuitive proof about why set of real number is uncountably infinite. See, why natural number set is countably infinite. Why natural number set is countably infinite? Because I am able to recognize each and every element. See, I will say that first number is 1, second number is 2, third number is 3, fourth number is 4, and so on. I am able to say which is my first number, which is my second number, which is my third number, which is my fourth number, and so on. Similarly, why z is countably infinite? Because I will be able to say which is my first number, I will say 0, which is my second number 1, which is my third number -1, which is my fourth number 2, then -2, and so on. Or you can say like this also: 0, -1, 1, -2, 2, -3, 3, dot, 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 dot. So I am able to say which is my first number, which is my second number, and so on. What about my real number? Can you tell me what is my first real number? Okay, so forget about first, second, third. I will just say real number between 0 and 1. Just try to give me idea about real numbers between 0 and 1. You will say first real number is 0. I am okay. What about my second real number? You will say 0.0001. I will say no. Actual first real number should be, sorry, second real number should be 0.00000001. I will say no. You will give me a smaller number, smaller number than this. You may give another smaller number than this, and so on. So I'm not able to recognize which is my second real number, which is my third real number between 0 and 1 only. So what about my this big giant set of real numbers? So obviously it will be uncountably infinite. Okay, and by now you may be able to guess about both the sets, countably infinite and uncountably infinite. Both are infinite sets, but countably infinite set is smaller set than uncountably infinite. So you may say that countably infinite is small infinity and uncountably infinite is big infinity. You can have just intuitive idea about it. Okay, so I hope I have made the point clear to all of you. So countably infinite is small infinity and uncountably infinite is a big infinity. Because real, you may get intuitive idea also that real number set is very, very big, very, very large as compared to natural number set. Okay, and in fact real number between 0 and 1 also is very, very large than natural number set. Okay, its size is larger than natural number set. Okay. So I hope I have made the point clear to all of you. Okay. So directly and indirectly, what I want to say that set of real number between 0 and 1 is also uncountably infinite, and so on. Please, I'm not going into more details. This is more than sufficient for you. Okay. So just try to note it down, and I'm jumping to next slide. Okay. Yeah. Next is set of irrational numbers is uncountably infinite. How will you prove that set of irrational number is uncountably infinite? I will simply say real number is what? Set of real number is what? Rational numbers. Rational numbers union irrational numbers. This entire set is real number. You already know all these things from your I think 7th, 8th class. So real number is what? Rational union irrational. Okay, so both are I think you may get confused. So I will say here rational, RA, rational union irrational. That is your real number. Now rational number set is countably infinite, and real number set, you know, it is uncountably infinite. I have already proven you. So what should be IR, or what should be irrational? Obviously, if it is countably infinite, then I will say, see, this is a theorem and I am not going into proof of it. Countably infinite union countably infinite, then obviously it will be countably infinite, because you are just union, you are unioning, you are doing union of two countably infinite sets. So this is countably infinite means what? There should be one-to-one correspondence between natural number set and this set. This is countably infinite means what? There should be one-to-one correspondence between natural number and this set. Now, if I union these two sets, then obviously we can establish one-to-one correspondence between natural number and this union of these two sets. Okay, you may think that cardinality will be doubled and so on. Please do not think about it. In case of infinity, I will roughly say 2 times infinity, 3 times infinity, 5 times infinity is nothing but infinity only. Okay, so I have given you intuitive idea. So you just, or if you are not able to follow, just try to remember it, that countably infinite union countably infinite, you will get a countably infinite set. Okay, you will not be able to get uncountably infinite. You will be able to get countably infinite only. Okay, so application of this can be like this. See, z minus union z plus union 0 set. Because in z minus it is nothing but negative integers, it is positive integers, 0 is missing. So union all these, you will get integer set. And obviously this set is countably infinite, this is countably infinite, this is countably infinite, and this is also countably infinite. So directly and indirectly, I have given you a verification about why countably infinite union countably infinite will be countably infinite. Now, okay, so hence you have got the idea that IR cannot be countably infinite, because if irrational number is countably infinite, then real number should be countably infinite. But I have already told you that real number is uncountably infinite, so irrational number should be uncountably infinite. Okay, just try to remember it. Please note it down. I am jumping to next slide. Yeah, so set of complex number is uncountably infinite. See, what exactly are complex numbers? I will say complex numbers are nothing but real number cross real number. Okay, so this is your number line, and you will say that, hey, this is your x-axis now, and this is your y-axis. So here you will imagine that the number is uh, with each and every number I will apply iota sign, and with these numbers I will treat them as real numbers. So what I will say, so the complex number will be like this: x plus iota y. So I pick here 3 and I pick here 4. So I will say 3 plus 4 iota. So what exactly we are doing? So roughly you may be able to imagine that we are doing cross product of real number and real number. Okay, so that is nothing but complex numbers. Now, real number is uncountably infinite. Obviously, these are same, na? Uncountably infinite. So uncountably infinite cross uncountably infinite. Obviously, you will get uncountably infinite. Okay. So I hope I have given you proof also. And let me tell you one thing more. Countably infinite cross countably infinite, you will get countably infinite. Do not go into proof. I'm just giving you idea, and intuitively you may be able to imagine this. Okay, so roughly you may say that this is countably infinite, so natural numbers, and this set we will have a one-to-one correspondence, and this is countably infinite, so natural number, and this set will have one-to-one correspondence. So total cardinality will be roughly you can imagine 2 times infinity. So infinity is same thing only. So we will be able to establish one-to-one correspondence between them also. So countably infinite cross countably infinite, we will get countably infinite, but countably infinite cross uncountably infinite, obviously you will get uncountably infinite, and so on. Please try to follow it. Okay. Now, see, these are very, very important theorems. Okay. Countably infinite, union countably infinite, countably infinite. Many questions have been asked like this. Countably infinite, cross countably infinite, you will get countably infinite, and so on. Okay. So directly, indirectly, I want to say cross product of two countably infinite set will be countably infinite, or cross product of three countably infinite set will be countably infinite, and so on. Okay. So next is 2 power countably infinite set is uncountably infinite. This is Cantor's theorem, and I'm not going into proof of it. So this means what? See, 2 power n. 2 power n is obviously uncountably infinite. So 2 power n means what? Set of all subsets. 2 power n means what? Set of all subsets of natural numbers. Okay. So I hope you remember about power set and all. So this is see S. So 2 power S is what? Power set. Power set means what? Set of all subsets of S. So similarly, I am saying S, n is natural number set. Na? So 2 power n is nothing but UCI. That is set of all subsets of natural number. Okay. So I hope I have made the point clear to all of you. Similarly, 2 power Z minus, this will be obviously uncountably infinite. Why it will be uncountably infinite? Because 2 power countably infinite set is uncountably infinite, and Z minus is countably infinite set. Similarly, 2 power Z will be uncountably infinite. Similarly, 2 power Q will be uncountably infinite. 2 power prime number set is uncountably infinite, and so on. Okay. So I hope I have made the point clear. 2 power odd natural numbers will be uncountably infinite, and so on. So just take any countably infinite set, take the power set, you will get uncountably infinite set. Please try to note it down. Yeah. So now mathematical part is over, and we have to start now your TOC part. That means sigma star is countably infinite, and so on. So I will start that in next class only. Okay. So just try to follow it. Okay, and then I will start these things in the next class itself. So countability actually has two parts. One is mathematical part and another is TOC part. So mathematical part is over till now, and we will jump to TOC part in the next class. Okay, thank you so much. Bye bye.